Hello everybody, myself Prasant Mukhopadhyay, faculty member, Electrical Engineering Department, Greater Kolkata College of Engineering and Management. Uh, in the last class, we have started our study of monostable multivibrator circuits using op-amp. So we have discussed the step-by-step how the op-amp monostable multivibrator, that is one sub multivibrator, has been designed. How to design it. So basically, we have started with the basic monostable multivibrator block diagram. That is a switching network. Of course, it's the RC timing network as a feedback, and how op-amp monostable circuit is being designed from starting from the inverting amplifier, then its operational procedure, and then changing the they say feedback path from inverting to non-inverting, where that is the op-amp Schmitt comparator, and where how it is being operated or how it is working. Okay, so then we have discussed basic op-amp monostable circuit by using with this Schmitt comparator feedback path. Okay, this one. So RC feedback network actually. Now this how it works. Then we have discussed the basic op-amp monostable circuit. Then we have discussed about the waveforms of monostable op-amp monostable waveforms. Then we have discussed about its time period. Then we have discussed charging recovery time, and then we discussed the RC differentiator circuit, how it works basically. This is the input signal, this is the output signals which will be used in the monostable op-amp circuit, op-amp monostable multivibrator circuit. So this will be added once again, and that will give you the final monostable op-amp circuit. So this one. So this is actually see this RC differentiator circuit we have added. Basically, first it was op-amp inverting amplifier. Then we have changed the feedback part from non-inverting inverting to non-inverting. Then we have given the RC feedback network. Then studied its function. Then we have added the RC differentiator circuit, and this complete your op-amp monostable circuit design. Okay, so with this this thing will be clear if we take an example like this. Example is that an op-amp monostable circuit is constructed using the following component: R1 equal to 30 kilo ohm, R1 equal to 30 kilo ohm, R2 again 30 kilo ohm, that is R1 equal to R2. This feedback resistor R 150 kilo ohm. This RC network, this C 1 microfarad, and if the op-amp monostable is supplied from a plus minus 12 volt, that is plus VCC 12 and minus VCC minus 12 supply, and the timing period is initiated with a 10 millisecond pulse, then calculate the circuit's timing period, capacitor recovery time, total time between trigger pulses, and the differentiator network values, and draw the complete circuit. So data given here, what is R1 equal to R2 equal to 30 kilo ohm, R150, C 1 microfarad, and pulse width equals to 10 millisecond. Okay, so with this we have to find the first timing period. So you have to find first find out the feedback fraction beta. That is, we have seen that is beta equal to R1 by R1 plus R2. So put this value of R1 and R2, you will get feedback fraction is 0.5 to 50% of the output is being fed back. Now time t equal to RC ln 1 by 1 plus R1 by R2, you will put the value here. So you will get this time constant t equal to point, time period is this equal to how much? T is 104 microsecond, millisecond, sorry, 104 104 millisecond. So now capacitor recovery time, discharging, that is equal to RC ln 1 plus beta by 1 minus Vd by Vcc. This is the power direct voltage, and this is supply voltage positive. So this, if you put here, this is given. This is also, it is 0.7. This you find, you got beta equal to 0.5, and RC 150, C is 1 microfarad. So put this value, and you will get the charging time will be 70 millisecond. Okay. Now total time. So total time between trigger pulses will be delay time plus charging time. So delay times you got, charging times you got 70 millisecond, and delay time is 104 milliseconds. So it comes to 174 millisecond. And input pulse given is 10 millisecond. Therefore, negative spike duration will be 10%. That means if we assume a capacitance value of 0.1 microfarad, then the differentiator RC values are calculated like this. Pulse width 10% per 1 millisecond, that is 5 RC. If C is 0.1 microfarad, R will be like this. From this, so we get, it is 2 kilo ohm. So this gives the final op-amp monostable circuit for the example as like this. Okay. So only we have put the values of this R1, R2, R, and C, and then RC differentiator circuit. This C, this is R, and this is the diode, of course, D1, this is D2. This is plus VCC, this is minus VCC, and this is your 10 millisecond input pulse, and this will be giving you the pulse output or delay pulse. And so that's complete the monostable by multivibrator circuit using op-amp. Now, so we find this from this lecture that op-amp monostable circuit can be constructed using general purpose operational amplifier. So that may be 741 and few additional components that we are finding here. While it may be easier to construct monostable or one-shot circuits using discrete components, like I told you in the very beginning of the discussion of this monostable multivibrator using op-amp. So it can be that, particularly this is the switching circuit, or the digital logic gates, or the common 555 timer IC, actually IC 555 timer chips. Something which is required to construct monostable multivibrator using op-amps for use in analog circuits. So by configuring an op-amp as a Schmitt trigger with positive feedback, the duration of the output pulse is determined by the time constant of the RC timing circuit, as well as by the ratio value of the resistive voltage divider network providing the positive feedback. which helps make the circuit unstable. And so with this, this will complete our discussion on monostable multivibrator using op-amp circuit. So if we give a quick recapitulation about the discussion of the total discussions on monostable multivibrator using op-amp, we see how step by step we have developed this monostable multivibrator using op-amp, and how we have say clear our say learnings with an example where we have with 741 op-amp with some components we have designed the monostable circuits, and we have found its say pulse, this time, etc. So this actually help us. Once again, I am going back to my earlier on the very beginning of this discussion. That will clear our idea. Once again, I am going back. See, actually, this is the very beginning. So what we have seen? We have seen that we can say construct this monostable multivibrator from using op-amp, or rather than op-amp, we can use say either digital say logic gate or something else, or transistor sensor also. So we or you can later on we have find that we can construct a monostable multivibrator with the use of 555 IC timer circuit also. So we have started with our discussion with this is the basic block diagram. RC timing network was connected across the switching circuit, and this is trigger input, and this is the trigger output. This is the unstable. This is stable state, and this is stable state. This is unstable. So now we have discussed monostable circuit starting with from inverting amplifier. Okay, and then this is the feedback fraction beta. This is voltage divider circuit. Now we have changed this feedback from inverting to non-inverting input part, and that will give you the study of Schmitt comparator. And we have discussed in details this Schmitt comparator circuits. Then we have found out the feedback fractions, the time period. Then we have with this Schmitt comparator we have say give the feedback circuit RC network here, and with that we have got the monostable multivibrator waveforms here. Then we have discussed its timing period of the monostable, then recovery time, charging time, etc. And that and lastly we have used the RC differentiator circuit, and that will be used to complete the basic monostable multivibrator circuit using op-amp. So we are coming this part. See, we have added this RC differentiator network. With this, first we have started, then inverted, and then Schmitt comparator, then RC feedback path. Then we use this RC differentiator circuit because its spike will be used, and this is the output. And everything has been cleared with this example. we have taken. Okay, we have calculated everything, and finally we have so far we have discussed about monostable multivibrator circuit using op-amp, and we have thoroughly discussed in the last class, and this class we have completed this monostable multivibrator using op-amp. Now we'll discuss bistable multivibrator using op-amp. Now basically bistable circuit can be used as convenient switches triggering on incoming pulses and remaining in that state until reset. So bistable circuit are widely used form of logic circuit, and this circuit can be built using a variety of different types of semiconductor devices. But since we are discussing the bistable or astable or monostable multivibrator circuit construction using op-amp, so this topic also will discuss how op-amp is being used to construct or design a bistable multivibrator circuit. A bistable means basically bi means both two. So it another name is the flip-flop circuits, and used for many applications when associated with analog circuitry. And the use of a comparator or op-amp can be convenient also. Now, what is bistable? Basically, a bistable is an electronic circuit, also referred as flip-flop or latch. It is a circuit that has two stable states and can be used to store state information. Okay. Once again, I'm repeating. A bistable is an electronic circuit, also known as a flip-flop or latch circuit, and it has two stable states and used to store state information. A bistable multivibrator or flip-flop can be made to change state by signals applying to one or more control inputs, and we'll have one or two outputs. So bistable has two stable states, hence the name bistable, and it can be flipped from one state to another by incoming pulses. Okay, this is very important. It can be flipped from one state to another by incoming pulses. So flip-flops and latches are a fundamental building block of any digital electronic system. One of their chief applications is in storing data, and as such they are widely used in computers and processor systems of all sorts. Okay. Now, how it is used? Op-amp is used as a bistable multivibrator. So very easy to use an op-amp or operational amplifier as a bistable multivibrator. And incoming waveform is converted into short pulses, and these are used to trigger the operational amplifier to change between its two saturation states. In our previous discussion on monostable circuit, we have seen this. To prevent small levels of noise triggering in the circuit, hysteresis is introduced in the circuit. That's what we have discussed in when we have studied the monostable multivibrator circuit, and the level being dependent upon the applications required, of course. And the operational amplifier bistable multiplier uses just here we have seen the 5 components. So 1, 2, 3, 4, 5. Okay, so this is op amp. 1, 2, 3 resistors and a capacitor. Yeah. So this is the basic simple bistable multimeter circuit. This is the trigger input, and you are getting here the output. This is the feedback part. This is differentiator. Okay, simple bistable circuit. The basic bistable circuit has 2 stable states. These are the positive and negative saturation voltages of the operational amplifiers operating with the given supply voltage. Actually, during discussion in details with the monostable multimeter, we have shown the saturation voltage say between plus BCC and minus BCC. So these are the positive and negative saturation voltages of the operational amplifier operating with given supply voltage. And circuit then be switched between them, applying pulses. Negative going pulse will switch the circuit into the positive saturation voltage. The positive going pulse will switch it into the negative state. That we have discussed in our earlier class portion. See, so this is the input and this is the output. This is positive saturation and this is negative. So this is the waveforms for the bistable multivibrator circuit. So it is very easy to calculate the points at which the circuit will trigger, at which point the circuit will trigger. Positive going pulses need to be greater than output saturation voltage. So the potential divider, yeah, it is given this circuit. Okay, so we can write this minus this saturation into R3 by R2 plus R3. See this circuit. Sure. Okay. So actually, this is the beta part. Okay. So and similarly, the negative going pulses will need to be greater than the positive saturation voltage B set saturation through the potential divider. That is positive B set multiplied by R3 by R2 plus R3. Okay. Yeah, it is. Yeah. So if they are not sufficiently large, then the bistable will not change state. When requiring switching circuit, comparators are normally better than op-amps, as they do not exhibit the tendency that some op-amps have to latch up. Also, comparators are much faster. So we have used the Schmitt comparators. That's set for some application and op-amp can work well enough. Okay, so with this we conclude our discussion on multivibrators using op-amp. Basically, if we sum up or say recapitulate our earlier all the discussions of this multivibrator circuit using op-amps, we have studied started with astable, then monostable, bistable, everything coming. Okay, so give a quick recapitulations of the overall discussions of multivibrator using op-amp. We have started with from here. We have started with patience, please. Yeah. So we have come up with this stable multivibrator circuits. First of all, okay. Yes. So we have studied this stable, monostable, and bistable multivibrator circuits using op-amp. This is all about the stable means two quasi-stable states here. It is also called free-running multivibrator. No external signal is required to produce the changes in the state. And the oscillator oscillates between two states, so it is used to produce a square wave. We have seen the production of the square wave. See, this is the feedback part. See, yeah, this is the template. So that's all about your stable. Then we discussed monostable multivibrator, which is a one-shot multivibrator, of course, it is called, or regenerative one-shot multivibrator, actually. We have discussed its, studying its block diagram, op-amp, starting with the op-amp inverting amplifier. Then we have Schmitt Comparator. Okay, just inverting in inverting and non-inverting terminal. I'm going to get this with the voltage divider circuit and so on, right here. Okay. So then we have introduce the feedback parts by which we have this construct basic op-amp monostable circuit. We have discussed in details about this, its waveforms, its timing period, then yes, charging time. Then we introduce RC differentiator circuit and we add it in the basic op-amp monostable circuits in the input side to generate the complete, see this one, to get the complete op-amp monostable circuit. Then we have taken out an example of designing for an op-amp monostable circuit and calculated everything. We have since, and this is the final monostable design circuit. And then finally we have discussed in short the bistable multivibrator circuits using op-amp. And here it's also called the flip-flop or latch circuit. This is the basic simple bistable multivibrator circuit. Okay, this is his input, this is output, which is varying between positive saturation voltage of the supply voltage and it is negative saturation voltage. And that's all about multivibrator circuit, because this timer switching and timer circuit is very important to study in the power electronics and drives. Basically, it's when we are talking about the controlled converter circuits in details. So this trigger pulse, how it can be generated and how it is useful to control the converter output. So that's why this circuit is very important. This study of the switching and timer circuit is important. In the next class we'll again discuss the same things by using triple pipe timer IC 555. So before that we will discuss about the IC 555 and then we'll discuss how it is used for multimeter.